And without further ado, please allow me to introduce Mihailo. We're just going to call him that, okay? I'm not going to pronounce his last name because I would just butcher it. Mihailo is a software architect by choice, an engineering manager by accident. 13 plus years in the industry has taught him stuff, and he wants to share it with you. So without further ado, take it away.
Thank you very much, Carl. I just want to mention it's an amazing pleasure being here because like couple of years ago, Dutch PHP was the first conference where I was supposed to speak ever, and it got canceled due to COVID. And I'm just tremendously happy to be back, even virtually. Now, let's jump right into it without wasting any more of your time. I will be asking some questions, so you can answer. Like you can virtually raise your hand by answering in the Slack channel, and yeah, let's give it a start. Now. Recommendation systems, quite a niche to be talking about, and one that I'm tremendously happy about. But before I jump into it, I just like to kind of ask you to write. I would ask you to answer it, but I would ask you to write like, what do you think? What was the first instance, or what was the first company or entity that actually pushed the development of recommendation engines? Like, just give your best guess and write it to a Slack channel. I'll wait for like 10 seconds because I'm curious to see what you think. So who was the first one, or what was it that triggered the expansion and development and investment? Yeah. So I don't really know. I'm not getting messages here. So if you said Netflix, you'd be right. Believe it or not, like before 2006, recommendation systems weren't even a niche. They were kind of like something in the circles of academia, you know, and nobody gave much care about it. But then in 2006, Netflix actually published kind of a contest where they asked participants if they could develop a better recommendation system that they had at the time. And the prize was actually, believe it or not, $1 million. And the competition took 2 years until 2008, believe it or not, so 2 full years. And the winning solution was actually 10% better than the Netflix's original recommendation system engine. And what it used to use is something that I will mention kind of near the end of this presentation, like the algorithm they used to use. Now, that's kind of the intro to give you an interest. And basically, 2008 is kind of the breaking point after which the recommendation systems start, you know, like a lot of investment, a lot of people start investing time into it, a lot of research goes into it, and basically the expansion of it and the popularity of it starts. And that's all cool, actually, but to understand where I'm coming from and why I'm talking about recommendation systems, I need to give you first a little bit of a background. Now, speaking of the background, I became a father quite recently, like it was 3 months ago. And it's, aside from being a challenging experience, and aside from wanting to brag a bit to you, the reason why I'm showing this picture to you is that, believe it or not, but babies are literally one of the best pattern matching machines. You know, like they come pre-built with pattern matching mechanisms ingrained into themselves. Like the moment they're out of the womb, they're like, you know, they can recognize the tit, you know, like, and basically anything that looks like a tit, they would start sucking on it, right? Which is great because it allows them to survive. Now, that's all cool, right? So the evolution at its best, babies being the best pattern matching mechanisms. But the problem is that the evolution can be a bit weird in a way. So they are not really, they have these pattern matching mechanisms, but they're not perfect. So we had a situation where my wife was holding our son in front of her, and she was like cuddling, and he literally tried sucking on her nose at one point, and basically had quite a bit of a time. And wasn't the most pleasant experience, but it just tells you that you know, even evolution can be wrong. And the reason why I'm saying that is because if the evolution can be wrong after all these like hundreds of thousands of years, you can allow yourself some slack in your machine learning algorithm or journey or whatever it is. Because you can allow yourself to be wrong with whatever you're building. Like the first version of your recommendation system or whatever you're doing with machine learning could be a bit buggy, but allow yourself some slack. Now, there was a poll actually, and most of the participants answered that they don't have, well, you don't have much experience or not that much experience with machine learning, just some basics. And that's actually cool, to be honest, because one really interesting thing about machine learning is that you can really get a long way without actually having any idea what you're doing. Like literally, basically just by playing around and trying stuff out, you can actually get the results which actually make sense. And that's actually cool because it's quite a rewarding experience to play with machine learning. And basically what I'm hoping is to inspire you a bit so that you can maybe try out something here and there, maybe build something. It might suck just like my son, but I mean his sucking journey, but it's a rewarding experience. Now, aside from being a rewarding experience, machine learning can be quite challenging. And it's not because computers are stupid. It's because humans are a bit not that precise as you might think. And I'll show you why. So take a look at this picture. And I can't see your faces, but I would imagine that it took you at least like, I don't know, a couple of seconds to actually understand that you're looking at a horse and a dog. So I mean, and don't even get me started with this image of like trying to understand what's like a fried chicken and what's a puppy, right? I mean, that tells you that even humans, even our intelligence can be a bit challenging or limited, or it takes time to understand stuff. So give some slack to your computer next time you're trying to build something, hopefully after this presentation. Now, when I signed up to do a talk about machine learning in PHP8, I honestly had no idea what I was going into. And I kind of believed that PHP can do a lot, but I never tried it. So basically, my application of this talk was actually the experiment. And what I actually learned is that what most people would say is that what's actually missing in PHP to make it a machine learning friendly language is the ecosystem. Like in Python, you have like a bunch of libraries. You have also R language. You have something in Java, but I never used it because, like PHP is better. Now, the ecosystem seems to be the most frequently used like excuse not to do machine learning in PHP. But, and this is perfect, to my surprise, I actually learned that PHP has two great libraries, like really mature and great libraries. Like one is RubixML and second one is PHPML. And basically, even though PHPML is a cool one to check out and basically see, because I think it's maintained by one guy or whatever, it's cool to play around. We will focus in this presentation on RubixML because it's quite mature. It has a lot. It has a lot. Just by going through the documentation, you can build a lot of stuff out of the box without having any idea what you're doing, and that's just great. You can sell yourself as a machine learning engineer or whatever. Now, in order to fully understand what we are talking about, I promise to give you a bit of introduction on some basics and a bit of a math. But I'll try to make it fun and interesting. So I'll kick it off with something that I'm pretty sure that most of you have, I would hope that you at least heard of, right? And it's called vectors. And I really hope that most of you at least heard of it. I mean, in the high school or elementary school, I'm not even sure where it started, but I hope some of you know about it. And there are some alternate names to vectors, and some call them 1D arrays, some call them rows, observations, samples, stuff like that. Tensors. So if you ever heard about TensorFlow, it's all about vectors flowing, stuff like that. And one might wonder, like, why we have so many names, like for the exact same thing, because everything that I specified here is absolutely the same thing. It's all vectors. And turns out that it's basically depends like where it originated from. Is it from math or from physics? And basically wherever it originated from, somebody came up with a new name. But I'll try to stick to the name vectors, but I just want to point out that whatever you see, like whatever name that you see, it's basically a vector, all right? Now, a logical question to ask is, what is a vector, right? And it really depends who you ask. If you ask a physics student, they would tell you, well, it's it's an arrow with a direction pointing somewhere in space, whatever, it has the length, tra-la-la. And if you ask a math student, he would tell you, well, vector is just an ordered sequence of numbers or whatever. And for the purpose of this presentation, we'll actually focus on what math student would tell us. So let's start with one-dimensional vector, right? So if we were to say like we have a vector with one dimension, 2, if you plot it, you can plot it on just one axis, right? And it's basically exactly where you would expect it to be, right? On the place of where 2 is. Now, if we go to 2 dimensions, it's basically like a 2D space. And this is a point like with 2 coordinates, 2 features, whatever you want to call it, 2 dimensions with points with dimensions 2 and 2, right? Now you can go 3D as well, right? And basically, technically after 3D, it becomes a bit challenging for humans to actually, for us to draw this, right? But mathematically speaking, math doesn't care whether you use 2 dimensions or 100 dimensions or 100 million dimensions. It's completely like irrelevant mathematically speaking, right? And that's why machine learning and computers are great, because they can use the vectors with million dimensions or whatever, and we can't picture it, but mathematically it doesn't make any difference. Now, for the purpose of the presentation, I'll just focus on 2 dimensions because it's just easier, like it's mentally easier to think and work with it. But just whatever I say is pretty much applicable to like infinite number of dimensions, right? So we have a point A, vector A with dimensions 2 and 2, and let's say we have another vector with dimensions 4 and 1, right? Now, if I were to ask you, how would you say how similar these 2 points are, right? Basically, one way to answer that would be just by observing. You could say, well, they seem to be close enough, but yet they're not the same. There is some distance, and they seem to be a bit away, and they seem to be pointing in similar directions, but it's not the same direction, whatever, right? Which is cool if you were talking to somebody and if you were explaining like how to find some street, you can tell them, well, you go that way and that and a bit of to the left, whatever, to the right. But in math, there is a better way, actually. And one obvious way, which might be obvious, which might have been obvious or not, is that you can just measure the angle between them, right? So basically, and specifically, we take the cosine. We will, for purpose of this presentation, we will be taking the cosine of this. So basically, when the cosine is 1, they are absolutely similar. Like they're exactly the same. And when the cosine, which is basically when the angle between them is 0, right? They're exactly the same. When cosine is -1, they're basically pointing in different directions, completely opposite directions. And that gives you an idea, I hope, right? So we will focus on cosine. And there are a bunch of other metrics like Euclidean distance, Manhattan distance, and funny enough, it really depends on the use case that you're working with. But what's really important to understand is that at the end of the day, it's all about how you compare the vectors, right? And I'll stick to cosine just because it's super simple to understand, right? Now, vectors are cool, but let me give you this is just like your typical math class. That's cool, but can you give me something tangible, right? Give me some real life example. So I'll give you a real life example. If you ever tried playing with, if you ever did anything machine learning related, you must have came around this iris species dataset, which is basically some guy went around and collected the samples of this iris flower, and he figured out that there are four characteristics that distinguish the family of this flower. And basically, based on this sepal width and length and petal width and length, you can actually say, based on those dimensions, you can pretty much say to which family of flowers the flower belongs to, right? If you took a random sample, you just measure these metrics, and you can say, well, it basically belongs to Setosa, versicolor, or virginica. I'll never get the naming right, but you get it, right? And this data set is basically a CSV file, but I just found a graphical representation, and it looks like this pretty much, so you have like each row is one sample, and each column is some dimension of it, and the last column is basically the family of this flower, right? Now, as I told you, like people call them samples, instances, observations, tensors, whatever. I'll just focus on calling them vectors, all right? Because they really are vector in a nutshell, right? And this funny thing right here, this table, it's actually, I think that's probably the only thing that everybody managed to agree on to use the single naming, and it's called a data set, because you have a data and it's a set, so it's called data set. Everything else nobody can agree on, but seems like every language and every science seems to agree that this should be called a data set, all right? Now, why am I telling you that? Well, that's because if we go back now or go forward to Rubik's ML, it has this concept of data set, and this is how you actually load this iris species data set, right? So you basically, it's actually like two lines of code, like specify the path to the CSV file, and second one is convert strings to numbers, and that's it. We got the data set ready. We'll literally, this is everything it takes to load the dataset in PHP, believe it or not, in PHP, right? Now, going back to our original dataset, the question that we ask is, how do we actually compare the vectors, right? How do we find the ones that are most similar to it, right? And it turns out that there is one quite cool algorithm, and it's called KNN. You might have heard of it, you might have worked with it, you might whatever, I don't know, but it's actually basically abbreviation of K nearest neighbors. Now, the name might sound a bit intimidating, like K nearest neighbors, all right, like time to escape this call, but it's actually quite similar. All this algorithm says is that you are as good as your neighbor is, right? Pretty much. So you're as similar as your neighbor is, right? And let me give you a real life example of KNN. So just take a look at this picture while I take some refreshment. So if I were to ask you like, who's part of which group, you can tell me immediately, right? You can say like this person is part of this group, that person is part of that group. And the way that you actually do that is by observing who's sitting close to whom, right? So you pretty much determine who's part of which group by actually determining to whom they're sitting the closest to, right? And that's exactly what KNN is all about. Like you give it vector and you find the n number, like n being 1, 2, 3, 5, 10, whatever, n neighbors, and you say, find me, I don't know, 3 nearest neighbors, and once you find the 3 nearest neighbors, basically, I'm definitely part of that group, or that iris species. And to do that in Rubik's ML is actually extremely easy, right? It's just 2 more lines, and specifically these 2 more lines. So you instantiate the estimator. You say that you want to look for 3 nearest neighbors, and then you train you train the algorithm against this data set, and basically you're done. After that, you can put the data into your model, into your like estimator, and you can basically classify the input data and get the classified data on the output, as you will see. And just to give you another hint before I show you how this works, basically by default, K nearest neighbors use the Euclidean distance, but you can specify cosine, Manhattan, Minkowski, or whatever. There are RubyXML has tons of estimators and tons of distance metrics. And as I told you, it's way more than experimental library. It's an amazing PHP library, and go play with it is my message. Now, speaking of which, so basically the task that you usually want to do is, given some data on input, given some vectors on the input, and here I have 4 vectors, right? Well, I have more, but you only see like 4 of them. Given some input vectors, based on the dimensions, I want to classify them, right? So basically, this is the input, and this is the output that my model gives me, right? So I just passed the data set to what I trained in the previous step, and this is the output that I'm given by the library, right? And this whole process is called data classification, believe it or not, because basically what you're doing, you're classifying the unknown data, right? And if you need a real life example, I'll just give you one: spam filtering, for example. Like if you can vectorize the email message, if you can turn it into a vector where like each row is one email and each column is something from that email, basically you can classify like 1 would be it's a spam, 0 is not a spam, right? Billions of examples of classification are there, and it's important to understand it because a lot of recommendation systems are based on it. Now, we are not talking about data classification, we are talking about recommendation systems here. So basically, let me introduce you to the first and the most simple way of building recommendation systems. It's called content-based filtering. And content-based filtering, because we are filtering, we are making recommendations based on some content that our data contains, right? And specifically for the purpose of this presentation, we'll be using the Movie Lens dataset. The Movie Lens is a freely available dataset that you can download. You can download a small or big dataset, it doesn't matter. But it contains basically the rows are movies, and you have a bunch of data. You either have some tags about the movies, or you have people ratings, you have tons of stuff. And the first thing I will focus on are the tags. So basically we have movies, and for each movie we have some tags. For example, for Terminator 2, these are some of the available tags, right? And each movie, there are like I think around 10,000 movies in the data set, and basically each movie contains a bunch of tags, right? Now, why is this important? It's important because if you look at the data is quite huge. It's a CSV file. It's quite huge. So I actually created like a really small representation of it. And this is how it looks like. You have basically a movie, and you have like what each movie is a row, and each column is some tag. And as you could predict, basically each row is actually a vector. We just vectorized the Movie Lens data set, and we created the features, right? So basically, the next thing that you want to do is you just want to use the classifier, and pretty much you just instantiate this. And let me give you an example. If you want to recommend movies to somebody, you would just say, like, what are some movies that you liked in the past? And based on some of the movies that person liked, you can just find the similar movies, and you're done, right? And that's exactly why every social website or social platform usually asks you for some interests the moment you register, right? Because there is this concept of cold start. When you're a new user and we can't recommend you anything because we don't know your preferences, well, the easiest way is to actually ask you what is something that you like, and based on that, you just use content-based filtering to actually recommend some other stuff, right? Now, that's quite cool and useful, but there is no much personalization in this, right? And in order to talk about personalization, because content-based filtering is all about like finding similar items. You know, if it's about movies, it's about finding the similar movies, but it doesn't take into account your personal preferences. And that brings me to the biggest difference between building the recommendation system and data classification system. So pay attention now. If you're sleeping, now is the moment to wake up, right? So on the left-hand side, you have a typical data classification dataset, right? Where each column is filled out, and basically the last column is the class that you're trying to guess, right? And basically everything is specified. When it comes to recommendation systems, it's basically you have just think about your typical Netflix user. Like, I don't know how many movies are there on Netflix, but I can guarantee you that most of the users only rate like a small amount of them, like 20 or whatever. Which means that if we have like 100,000 movies, each user would have rated only a part of only a small subset of everything available, right? And the data set usually looks like this, something like this, right? So you have users, but they actually don't have all dimensions specified. And the problem with this is that now you can't really use data classification, right? Because this is called, by the way, a sparse matrix. So recommendation systems are all about working with sparse matrices. Like, how do you take the sparse data and convert it into something that can be useful, right? So going back to the to our example with users, so by looking at this, all right, you can say that basically user 1 and user 6 are similar, right? Because by observing, you can see that both of them liked Game of Thrones and Breaking Bad. So basically, just by finding a user that's similar to user number 1, you can actually recommend to him like Money Heist, because user number 6 seems similar to us, and basically everything that he liked might be something that we might like, right? Like Money Heist, Squid Game, Peaky Blinders is definitely something not to recommend, and stuff like that, right? Now, we can fill out, that's one easy way to actually fill out the matrix. Like, find the users that are similar to our user and then fill out the matrix based on that. And once we fill out, we actually have a complete matrix, and we can just find whatever, like ratings 4, 5, and recommend whatever is higher than some threshold, right? Now, how do we do that with a lot of data and with a lot of dimensions, right? Well, if we go back to this example, basically it's all about applying the KNN to our matrix, right? So finding the nearest neighbors. So how do we do that? I'll show you. It's actually quite easy, to be honest. So basically, you load the data set, and as you can see, I have 600 users and almost 10,000 features, and features are movies, right? Now, I'll just take as a random example, I'll take user with ID 5, all right? As you can see, he rated only 300 movies out of 10,000. So there's not much data. So if I were to build a recommendation system and recommend stuff to this user, in order to do that in PHP, actually, it's way easier than you might have thought. So basically, I would just go through all users, and for each user I could compute the cosine distance, all right? And basically then I find the users with the smallest distance, I sort them, and basically I just take whatever these users, like 62, 57, I take whatever they rated, and I recommend that to myself. And code for that could be a bit intimidating, but what I'm really doing is I just took the most similar users, I found what are the most commonly highly rated movies that they rated, and I'm just taking like top 10 and basically recommending to my user. All right. So this is what this code is doing in a nutshell. And the output of that is quite simple and quite useful. Basically, we would recommend to our user to watch Grumpy Old Men, forums, whatever. Right. That right there is your first personalized recommendation system. I mean, if you expected something super uber complex, it's not really. And what I just showed you is called collaborative filtering, right? Basically, because you're collaborating and you're using other users to find basically similarities and to find movies that to recommend to myself, right? Now, I mentioned at the beginning of this presentation that Netflix, like the algorithm that won the Netflix prize, is something that I will mention. So we introduced so far content-based filtering and we introduced collaborative filtering. Even with these two, you can get a long way forward. I mean, like these two, you can build enormous things just by combining these two. But there is something more deeper, and it's actually a bit more complex to understand at first. But if you give it enough time, and if it settles down, and basically if you follow what I'm saying, you might actually understand it and see that you can build quite powerful stuff quite easily. So let me show you. So going back to this example of data classification versus the ratings matrix, right? So I told you that the ratings matrix, like the one on the right, is basically problematic because it's sparse, right? It's basically missing most of the data. Like for each row, there is a lot of data missing, right? And interestingly enough, if we could find a way to convert it into a into a matrix that's fully specified, we could actually use any data classification algorithm to build a recommendation system. And data classification, I already told you, it's something that has been like researched way more than recommendation systems. And the guys who actually, well, the guys, not the gals, who built the winning algorithm and who won $1 million actually used a technique. Well, basically relied on a technique called dimensionality reduction. And it sounds, again, intimidating if you never heard of it, but it's really a simple concept in a nutshell. There are these mathematical algorithms called dimensionality reduction algorithms that literally allow you to go from, for example, 1,000 dimensions to reduce to 4. And what's really cool about this is that the moment that you actually go from that you reduce the dimensions, you end up with a fully specified matrix, right? Now, obviously, like, easier said than done. A lot to be said about it, but what's something that I'm hoping that you can take from this presentation and hopefully investigate further are two main algorithms for dimensionality reduction. And they are called PCA and SVD. Basically, the first one is a bit easier. The second one is what was used by Netflix winning algorithm to outperform the original algorithm. But they both kind of rely on the same thing. They're trying to find some hidden preferences. For example, if we're talking about movies, if you rated like a number of movies, your hidden preference could be that you're into a sci-fi or romance movies or romance sci-fi movies. Those are those hidden attributes that are not visible in the initial matrix, but by applying the dimensionality reduction, it actually tries to find these eigenvectors that actually basically represent your hidden preferences. And based on those hidden preferences, you can actually build the recommendation systems without even knowing what your data represents after the dimensionality reduction. That was like super huge and long sentence, but trust me, once it settles, it's quite easy and quite simple. Now, what it's all about is all about going from the right to the left, right? Like you go from the sparse matrix to a fully specified matrix. Now, I'll show you a code that actually does that. Don't get scared by it. It's basically you load the data, you instantiate the transformer. I'm using PCA in this example, and I'm reducing from 10,000 dimensions to only 10 of them. And what I'm doing here, and again, this is a bit challenging part. Basically, what I'm doing is for each movie, I'm taking each feature out, then I'm reducing dimensions of the remaining, and I'm putting that, it's quite complex, I can understand, but I'm reducing the dimensions, and then I'm putting that movie as something to be recommended against, right? And this is basically the code here that you're seeing. And this is pretty much the code. Basically, so what you do is for each movie, you take each movie, you train a model against it. So basically, we end up with 10,000 models because we have 10,000 movies. We end up with 10,000 models, and basically, then we can use that to use as recommendations against this. Quite a complex topic, I understand. don't be scared by it. If you go and investigate and slowly build up, you will eventually get to understanding this one. And once you do, it's quite powerful, as I told you, especially when combined with some other stuff. And also the Netflix white paper is publicly available. You can check it out. You can learn from it. It's written in a very human-friendly language. So I would definitely advise you to check it out. And we are almost at the end. I mean, the time is quite limited, and I'm sure that you're almost a bit tired. So I just want to tell you that if you want to learn more, and I hope that I inspired you at least a bit, because my initial idea was to inspire you and to give you some directions. If you want to learn more, one of the best resources is basically rexis.acm.org. It's basically a conference that's held every year that's dedicated only about it's focused specifically on the research in the recommendation systems area. And it's held every year, and there's like tons of resources to learn from. And what I also discovered quite recently is that they have the YouTube channel where you can actually watch all the presentations from every conference, and you just wouldn't believe it what people are doing with the recommendation systems and what's all there is out there that is being built. Now, with that was quite a lot. So I'd like to actually thank you very much. You don't have to use this QR code. You can just use the usual ratings that you use for all other presentations. You can find my blog here, where I'm blogging about everything from mental health through newborns, which is quite connected, all the way to recommendation systems and machine learning. My social media is I'm quite communicative. Feel free to approach. Feel free to whatever. Reach out. And that would be about it. I would be happy to see if there are any questions, and I'll stay around, obviously, on a Slack channel if you want to chit chat privately or whatever. And with that, thank you very much.
Wonderful job. You're going to have to pause for a moment while I go and pick my brain up off the floor, because just some of the stuff that you were going to do. I got into programming for business programming, because business programming, like accounting and stuff like that, didn't use cosines and things like that. So I got a little bit lost there, but that is a great talk. I can't wait to watch that a couple more times and play with it, because I'd love to see PHP take a prominent role in the machine learning area.